in my class anyway, and we're using the textbook, of course, because why not? And we're going to get into what the chapter 2, section 5 calls reasoning in algebra and geometry, and what everyone who's gone through this before knows it as proofs. Oh yeah! So this is where we start arguing. I have talked about this in the beginning with my classes about arguing, but that's what we're going to start getting into. We're going to argue, but we're going to argue things very systematically, very logically. The disclosure right now is that if you're not in my class and you're watching this, sorry to tell you, but I am only doing an accompaniment to a set of notes on PowerPoint. Okay, so I have notes on PowerPoint. It's all on the Edmodo, and you have to learn about all these different properties. Okay, so we have the different properties that we're using of equality, properties of congruence, and we're using all of them, and there's a whole PowerPoint. I'm not going to spend time in the video with that. What I am going to spend time in the video is doing the accompaniment for that set of notes. And I'm going to start with this. Okay, so I have basically, we're going to identify the properties that are being used here to justify each step. Okay, and that's how we're going to fill this. This is part of the notes, but I want to fill this out for folks to see, how's this whole thing working. All right, so we're going to talk about properties that are being used, and we look at column or row 1. We have column 1, and it says 6n plus 9 equals 15. And in column 2, it says this garbage, right? Like what is going on? And all we have to do now here is identify the property being used. And so in that PowerPoint I mentioned, we have all this list of properties, and what's happening from column 1 to column 2 is, check this out. Look at the left-hand side, 6n plus 9, and look at the left-hand side now. 6n plus 9 minus 9. Whoa. And then look at the right-hand side, 15. Right-hand side, 15 minus 9. What's happening? We are subtracting 9 on both sides. So if you see what's going on, we are subtracting 9. And so what that means is we're using the property called the subtraction property of equality. Okay, the subtraction property of equality. And yes, you need to call it the subtraction property, and you need to call it of equality. Okay, so you'll see why. If you haven't looked at the notes, there's going to be a difference between equality and congruence. So now we go into row number 2. We have segment JK is congruent to segment GH. And so guess what? Segment GH is congruent to segment JK. And so what is going on here? And if you look at the two statements, they're just kind of like flip-flop. It's like they folded over each other. And if it looks like they folded over each other, that is called the symmetric property. Okay, so we call that the symmetric property. But we have to be specific now. Is it the symmetric property of equality? No. Is it the symmetric property of congruence? Okay, so we have to be particular in what we're calling, because we have to be really careful and sharp with our words. All right, so now for the third column, this is read angles. We got angle QRS is congruent to angle UVW, and angle UVW is congruent to angle XYZ. So column 2 says angle QRS is congruent to angle XYZ. What just happened? So we got to look. Well, here's QRS and here's QRS. That's interesting. Here's XYZ, here's XYZ. So it's like we just cut out the middleman. If this is congruent to this, and this is congruent to this, therefore, this is congruent to this. And that is a thing. That's a property. It's a logical step, and it's called the transitive property. Okay? So we call that the transitive property, and now we think the transitive property of what? Okay, this is of congruence, not equality. Okay, so this is the transitive property of congruence. Okay, so now we're understanding those notes from the PowerPoint a little bit better. Okay, now on to the fourth row here. We have, how do we read this? The measure of angle 4 is equal to the measure of angle 9. So we have to remember how to read that. Okay, so the measure of And then look at the next thing. Well, what do we do with this? This is showing, well, then the measure of angle 4 plus the measure of angle 1 is equal to the measure of angle 9 plus the angle of 1. What do they got in common? What's happening is that we're adding the measure of angle 1. And if we're adding something to both sides of an equation, we are using the addition property, okay? The addition property of what, right? Is it congruence or equality? Well, we're using an equal sign, that is equality, okay? And so that's how those all those notes kind of play out. So now we're going to move on to the next thing. Now what we're going to do is write a new congruency statement. All right, but in these two exercises, we're gonna definitely use the transitive property. If A equals B and B equals C, then A equals C, right? Or if A is congruent to B and B is congruent to C, then A is congruent to C. That's the transitive property. Okay, so we're gonna use that logic here and then write the next statement. So number 5, we got angle DEF is congruent to angle ABC, and angle JKL is congruent to angle DEF. Well, what's the congruency statement? What's the transitive property? We got a DEF here and a DEF here. That DEF is the middleman. Okay, so DEF is the middleman. We can just cut out the middleman, right? So therefore, we can totally say that, well, angle ABC is congruent to angle JKL. That is the transitive property, is that when we use those two little truths, we just cut out the middleman. Okay, so we can totally say that. It's reasonable. All right. Similarly, we have segment RS is congruent to segment VW, and segment RS is congruent to XY. What's the congruency statement? Well, where's the middleman? We got an RS here and an RS here. Everything's congruent. So RS is here and RS is here. That's our middleman. So we can cut out the middleman. And we can totally say that these two segments are congruent. So we can say segment VW is congruent to segment XY. Right? And that's how we use those properties. Okay. Okay. So now onto the next thing that needs some explaining from that PowerPoint. Okay. The next thing that needs explaining from the PowerPoint is this little thing. So we're gonna justify steps when we're solving equations. Okay. And so we went over all the different types of things in that PowerPoint, but let's look here. Okay. So what's happening here? We have we're looking for the value of x, and the only thing we know is that ray AB. And we got to point to that. Where's ray AB? A-B-O. Okay. I see it. Ray AB bisects angle R-A-N. R-A-N. Okay. And we remember what bisects means. Bisects means cut in half. Watch out! Okay, so we got to remember that. Okay, so what are we doing here? We're going to find the value of x, and we're going to justify every step. Okay, so the very first thing that we can do is, as we look at this, the very first thing that we can totally do is say, we can say, you know what? X is equal to 2x minus 75. We can say that this is equal to this, right? But we got to justify that. How can we say that? Well, that's the definition of a bisector. And then we would write that as our justification. We would write definition of bisector or angle bisector. Okay, so that by definition, the definition of, I should probably do angle bisector because we are going to be impeccable with our words. So the reason why we can say this, that is the definition of an angle bisector. Remember the given, it bisects that angle. So bisector means the two little parts are equal. Okay. So what else can we do? From here we can do a whole bunch of stuff. Now we're going to solve for x, right? So we have our units of measure. We have x's and ones. We have our ones already here by themselves. So I'm going to get my x's together. But I'm not going to show my work. I'm just going to do this. This is what I'm going to show, right? This is what I'm going to show. And you would have to justify that. And you would look from here to here and you would say, what the heck did Mr. Katz just do? And well, I did work. I'm just not showing it to you. Okay? I did work. I'm just not showing it to you. So what can you do? Figure it out yourself. See what happened. Okay, what I did without showing you was I undid 2x from both sides. That's what I did, but I'm not showing you that. Okay, so I'm saying 1x minus 2x's leaves me in the negative, right? If I have an x and I take away 2x's, I'm in the negative. So I'm like negative 1x. And then that's equal to what's left on the right-hand side, negative 75. So that's all I've done, right? But I didn't show that work. I'm just giving you this. You're the one that has to fill in the blank. You would look at that and you would say, oh my God, what did Mr. Katz just do? Oh, it looks like he subtracted 2x. Okay, so what did he just do? He used the subtraction property of equality. Okay, so remember the notes from the PowerPoint, the subtraction property of equality. That's what he just did, okay? And so we have that, but I'm still not done. So the next thing I'm going to show you is this step. I'm not going to show you any work. I'm just going to say this. Well then, x equals 75. You'd better justify that, right? So what did I do? What happened from here to here? Okay, so you have to think, what in the world just happened? And you have to know what just occurred. Now we could do one of two things from here. We could either divide or multiply by negative 1. It doesn't matter. You can divide or multiply by negative 1, and then this would become positive, and this would become positive. So it doesn't matter how you visualize that. If you're thinking that you multiplied both sides by negative 1, then you would write the multiplication property of equality. If you think that we divided both sides by negative 1, you would write the division property. I personally don't care, so I'll say division property of equality. Why not? Okay, so that's how we justify steps. Okay, so that's how that works. Cool, good, great, grand. Next. All right, so that's that note in the PowerPoint. And we're done with that guy. Now, part of the PowerPoint is this as well, right? So we're going to try writing a 2-column proof, okay? A 2-column proof. This is where things get interesting, okay? So the 2-column proof, we have this segment diagram here, and we have write 2-column proof. Given segment AB is congruent to segment CD, so what we have to prove, we have to argue, is that segment AC is congruent to segment BD. We're going to argue that. Okay, so this is all we're given. AB is congruent to CD. We're going to prove that AC is congruent to BD. We're going to argue that. Now, normally when you argue, you begin with what is given. Okay, so what is given? We have what's given. Well, segment AB is congruent to segment CD. That's totally given. We give you that, and that would be your justification. So we write that down, and, well, justify that. Okay, it's given. Done. Okay? Now we got to start thinking. How in the world are we going to approach this thing? Okay? So first thing we need to start doing is get out of working with congruency and get into working with equality. If we start working with equality, a lot of things are going to be better. So how do we make the leap from congruent to equal? Well, if the two segments are congruent, what do we know? The two measures are equal. So we can write this. We can say that the measure of AB is equal to the measure of CD. Okay, so notice what just happened. We went out of congruence and we went into equality. So how do we do that? What is the justification? How can we argue that? We argue that by saying congruent segments have equal length. We can totally say that. Congruent segments have equal length. Okay, that is legitimate, an argument to make. You can't debate me on that, right? No one can. It's solid truth. That's good argument. Okay. So now we keep thinking. Okay, so we know that AB is equal to CD. We can do a bunch of things from here. From here, things can go all sorts of directions as long as you're justifying each step. Now I'm keeping an eye on the distance between AB and CD, and I want to somehow get to AC and BD. So I'm going to start looking at AC. How in the world can I get to AC? Okay, well, I want to follow suit with this as much as I can. I want to keep, if I'm working with AB, let's keep AB there. So I'm going to keep AB there. And I'm going to say, okay, the measure of AB you know what? If I take the measure of AB, and I want to start working with AC, right? I want to get to AC. I want to get to AC. If I start working with AB, and if I add the measure of BC, right? If I add this measure here, you know what I'll get? I'll get AC. And that's what I want to start getting into my proof. I see the end in mind. And so I make that statement, right? AB plus BC, of course, is AC. How do I know that? Well, freaking prove it, cats. I don't need to prove it. It's a postulate, bro. It's the segment addition postulate. Remember that caveman math piece? The segment addition postulate. And that's my justification. Okay, so when we go through that, we're justifying. Justify. Okay? Now I have my eyes on AC. That's what I want, right? I have my eyes on AC. Now, I want to start getting into BD somehow. So what part of AC shares a part with BD? Right? So I need to start thinking. I got my AC. I need to get my eyes on BD. Do they share anything? Yeah, dude, they share BC, right? So how can I get access to this BC thing? There's my BC. So let me use BC. Okay? So you know what I know about AC? If I know, or AB, you know what I know about AB? AB and CD are the same because I have it here. So if I take this AB and I kind of switch it out and I call that ABCD now, I can call it that. That's the only thing I've changed. So the measure of CD plus BC is equal to AC. Look at what stays the same. I'm trying to systematically move into this proof. AB is the same thing as CD. How do I know that? I know that from here. Okay? And if I know that from here and I'm making the switch there, how can I do that? The justification is simply substitution. Okay? Substitution. So I can completely do that. Legit concern. Okay? All right. So now I got my AC all set. Okay? So I know what is AC. CD plus BC is AC. I know that. CD plus BC is A. Whoa. Now, like, from this step, you should be able to see the end. It's like, oh, it's right there, I can see it. CD and BC is AC? Wait a minute. CD and BC is BD, bro. What's going on? So you can see the end coming, right? So let's make that statement. We can say that, well, CD and BC, you know what that equals? It doesn't equal AC like 4. It equals BD. Yes, it equals BD. So the measure of this segment, and how can we make this claim? How do we know that? CD and BC is BD. How do we know that? Segment addition postulate. Okay, we can totally do that. Now, I've said this before, and I'll say it again. There are many other ways that we can prove this. Okay, I'm just using this way. You can do this any other way. But you want to be able to see the end in mind. Okay? We're arguing. Now we have something set up. Take a look at this. We have CD and BC and CD and BC. Do you remember the transitive property? Yes, I hope so. So if we have this and this, guess what? That's the middleman. If this is equal to something and this is equal to something else, it's the middleman. We can cut out the middleman. We can completely now say that, well, AC is equal to BD. We can say that. And how do we know that's true? We've cut out the middleman, and that's using the transitive property, okay? Transitive property of equality, okay? So we can do that. Isn't that neat, right? So you're arguing, and you're arguing to a point where you can't be denied. Now, look at where we are. AC is equal to BD, right? AC is equal to BD. Isn't that what we wanted to prove? We wanted to prove that, but in the proof, we're dealing with congruence. And here we have equality. So we need to clean up our mess, okay? We need to clean up our mess. Right now, we're dealing with equality because we're dealing with measures. We need to prove congruence with segments, okay? So now we can prove congruence with segments. And what is our justification for that? Well, guess what? Segments with equal length are congruent. Right? You're thinking, do I really have to say that? Well, yeah, actually you do. Segments with equal length are congruent. Okay, we got to write that all out. And now we have proven. Segment BD, done and done. Mic drop. Bam. Right? You cannot argue this because you have justified everything. You can't argue any statement. Like if anyone asks you why, just say keep reading. You'll see why. Okay? And so that's how that works. All right, so that's how all that stuff works. And I'll just quickly go over this. You got to pay attention. I'm not going to write this all down. If you look at the exercises here, we're going to prove that x equals 13 in this exercise, right? So the statement, QS is equal to 42. What's the reason? Given. And we can write that. We can write given. Okay, so maybe I will write this down and make it quick. Okay, so if I look at question 1, that's given. I can say that, right? All right, so now question 2. If that's given, right, if QS is 42, then I can say that QR plus QS, or QR plus RS is equal to QS. QR plus RS is equal to QS. How can we make that statement? Remember, that's caveman math. So we can totally call that the segment addition postulate. It's a popular postulate, isn't it? Yes. Okay. The segment addition postulate. The thing we knew before we could speak to one another. So now we move on to number 3. Whoa. How we get from letters to algebra? So this is QR plus QS equals QS. So we have QR plus RS, QS. X plus 3 and 2x is 42. What? Well, take a look at the diagram. QR, oh, it's x plus 3. X plus 3. And RS is 2x. And QS is 42. That's what we said. Okay? So what have we done in number 3? We have simply substituted equal values. So substitution. That's the reason. Okay? So how is the reason we could say number 3? Substitution. On to number 4. So we look for number 4. Now we go from here to here. What in the world just happened here? The 42 stays the same, but all this stuff got crumpled in. We simplified. And when we simplify, we have used the distributive property. Okay? So in number 4, the argument is that we've used the distributive property, which is legitimate. Right? We can totally do that. So now that we've used the distributive property, let's see what's going next. So here we are, we're at number 4. Now we're at number 5. What just happened? What just happened? We have 3x plus 3 here, and then the plus 3 is gone. How do you get rid of a plus 3? Subtract it. So what do? We subtracted. What property is that? The subtraction property of equality. Okay? We're dealing with equality now, right? So we have to say so. The subtraction property of equality. That's how we got to number 5. We have to say that. And then we look at number 6. Number 6. All right, so, whoa, here's number 5. How in the world? We had 3x here and then just 3 here. How did we get rid of that 3? We divided. So the final thing we did is the division property of equality. Okay, division property of equality. And so that's how we begin working with proofs. Okay, and this is just, again, to supplement to that PowerPoint. A lot of stuff to think about, and that's good enough for now. I think we're cool. So I'll catch you on the flip side.